In the last few hours, a number of individuals have reported that the University of Utah's live Yellowstone seismograms have unexpectedly gone offline. Oddly enough, this groundbreaking news arrives just hours after national park officials admitted a major oversight in their monitoring of seismic activity at Yellowstone National Park. In a surprising turn, scientists have revealed that over 86,000 earthquakes have occurred beneath Yellowstone, a number 10 times higher than previously believed. This dramatic update came after researchers began using artificial intelligence to scan seismic data collected between 2008 and 2022. The announcement has sparked widespread curiosity, especially because officials had just acknowledged they had significantly underestimated the number of quakes occurring in the region. Some are wondering whether the timing of these announcements suggests the park is even more geologically active than previously assumed. With this new data now available, scientists and the public alike are rethinking the story of Yellowstone's restless underground. The timing of the seismograph outage has raised eyebrows. Some who have followed the data streams for years have remarked that the downtime feels oddly coincidental, aligning with what they describe as an increase in subtle tremors and underground movement. These observers have begun to wonder whether the interruption is due to routine maintenance, technical issues, or something more deliberate. A few even suggest the data may have been intentionally hidden to prevent public concern or speculation. Though no official explanation has been provided, the incident has sparked fresh conversation online about transparency and the potential risks associated with Yellowstone's supervolcano. Many have voiced growing concern that the threat level at Yellowstone should be raised to high due to the recent revelation of over 86,000 previously unaccounted for earthquakes beneath the caldera. These quakes suggest that the region is far more active than we are being told. Regarding the recent earthquake study, scientists working in collaboration across 3 major institutions, the University of Western Ontario, Industrial University of Santander in Colombia, and the United States Geological Survey, have revealed that over 86,000 earthquakes have been detected beneath Yellowstone National Park's iconic caldera using artificial intelligence. This discovery is reshaping scientific understanding of the geological dynamics occurring beneath one of the world's most closely monitored volcanic regions. Until now, the full extent of Yellowstone's seismic activity was largely underestimated due to the limitations of traditional monitoring methods. This new finding spans data collected between the years 2008 through to 2022. Using artificial intelligence, researchers were able to comb through extensive seismic records with a level of precision and speed that human analysis could never match. The results showed a staggering 10-fold increase in the number of earthquakes compared to what had previously been documented. This development suggests that the Yellowstone caldera may be significantly more active than once believed. The integration of artificial intelligence into geological research marks a turning point in the way scientists study the Earth's underground movements. Traditionally, seismologists had to manually sort through endless charts and waveforms to identify seismic activity. This process, though thorough, was painstakingly slow and prone to human error. Many subtle events, particularly those that did not produce dramatic or easily identifiable signals, were overlooked or misclassified. The advent of artificial intelligence allows researchers to detect even the most nuanced vibrations in seismic data, revealing a previously hidden world of microquakes and seismic patterns. Professor Bing Li, one of the study's lead authors and an engineering expert at the University of Western Ontario, explained the benefits of using artificial intelligence to manage this overwhelming data. He noted that manually processing such large datasets would be nearly impossible, describing the traditional approach as unscalable. By leveraging machine learning, the researchers developed algorithms capable of identifying not only isolated quakes, but also seismic swarms, clusters of small, interconnected earthquakes that unfold across time and space. These earthquake swarms are especially intriguing. Unlike a single strong quake that lasts a few moments and then ends, swarms unfold more subtly, emerging over days, weeks, or sometimes even months. They consist of numerous minor quakes that ripple through fault lines without a singular dominant event. These swarms are believed to be triggered by the movement of underground fluids, primarily water and gas, interacting with geological faults. Though typically not strong enough to cause surface damage, they are critical indicators of subsurface processes, and can provide insights into how pressure builds and disperses beneath the Earth's crust. The AI's success in identifying these swarms means that scientists can now study seismic patterns in greater detail. By understanding how these swarms behave, researchers can gain insight into how fluids move underground, how faults interact with one another, and how pressure accumulates in volcanic systems. These are all key factors in understanding potential volcanic activity. Professor Lee further explained that this refined understanding of seismic patterns holds practical value beyond academic interest. Knowing where and how these swarms occur allows scientists and public officials to better assess risk and safety for people living near or visiting Yellowstone. It can also guide the development of geothermal energy by helping energy developers avoid drilling in areas with unstable fault networks or excessive fluid activity. The Yellowstone Caldera itself is a vast depression measuring approximately 72 by 48 kilometers, around 45 by 30 miles. It was formed roughly 631,000 years ago during a massive volcanic eruption that emptied a large magma chamber beneath the ground. When the magma chamber collapsed, it created the sunken landform now known as the caldera. While the region has not seen a cataclysmic eruption in modern times, it remains geologically active and is one of the most studied volcanic features in the world. According to the new study, many of the earthquake swarms occur along what scientists describe as rougher and less developed fault lines within the caldera. These are compared to older, smoother fault lines found outside of the main volcanic region. To determine the roughness of these faults, the team applied the mathematical concept of fractals, patterns that repeat themselves at different scales. This concept is seen in nature through snowflakes, coastlines, and even the branching of trees and blood vessels. Fractals allowed the team to measure the degree of irregularity in the faults. What they found was that more irregular fault lines inside the caldera were more prone to seismic swarms. This, combined with other data, suggests that underground water moving slowly through the Earth, along with occasional bursts of pressurized fluid, may be key drivers in triggering these clusters of earthquakes. While this doesn't necessarily imply an imminent eruption, it does point to a much more dynamic and complex system beneath the surface than was previously understood. Professor Lee also emphasized that while scientists cannot yet predict exactly how one earthquake might lead to another within a swarm, having this expanded dataset opens the door to new kinds of statistical analysis. These models can help identify patterns, test hypotheses, and refine our understanding of Yellowstone's subsurface processes. The research marks a leap forward in being able to observe and quantify earthquake behavior in regions of volcanic interest. Published in the prestigious journal Science Advances, this study is not only a scientific milestone, but also a reminder of the vast potential artificial intelligence has when applied to earth sciences. While the data itself may seem technical or abstract, the implications are profound. Yellowstone is not just a scenic national park. It's an active geological system sitting atop a supervolcano, and its movements affect both the scientific community and the general public. Public interest in Yellowstone has surged over the years due to its geothermal features, historical eruptions, and frequent earthquakes. News of heightened activity often captures the attention of both scientists and enthusiasts who track the caldera's behavior for any sign of significant change. Now, with this new assisted data, observers have more information than ever to monitor developments in real time. In a broader context, this research highlights how interdisciplinary collaboration between geologists, data scientists, and engineers can bring about revolutionary discoveries. It also reinforces the value of artificial intelligence as a tool not just for convenience, but for uncovering truths that human effort alone may never have discovered. Though this research does not suggest that a volcanic eruption is imminent, it does reinforce the need for constant vigilance and the development of advanced monitoring systems. The Yellowstone caldera is a natural wonder, but it is also a sleeping giant whose subtle rumblings deserve close attention. Thanks to artificial intelligence, we now have a far more complete picture of its restless nature. As researchers continue to refine their models and apply these methods to other areas of the world, it is possible that similar increases in earthquake detection could be made elsewhere. This may fundamentally alter how we understand volcanic systems, fault behavior, and the broader mechanics of the Earth's crust. Recently, the park has experienced a swarm of earthquakes, drawing attention from scientists, tourists, and the general public. These seismic events have raised concerns about the stability of the Yellowstone Caldera, often referred to as the Yellowstone Supervolcano, and they come just days after tourists at Yellowstone National Park managed to film the terrifying moment when a massive explosion occurred, causing them to flee in fear for their safety. The footage reveals numerous guests quickly evacuating a boardwalk located dangerously close to a scorching hot spring. Biscuit Basin has been completely closed off by the National Park Service as geologists conduct an investigation into the incident. This occurrence once again prompted speculation on the potential impact of these earthquakes on the national park. Some individuals who examined the data provided by the United States Geological Survey have noted the absence of certain portions. For instance, they reported that on certain days, only a few hours of the day were displayed, while the remainder was left unaccounted for. Consequently, certain individuals questioned whether certain information was being withheld. While the United States Geological Survey has acknowledged the occurrence of these minor tremors throughout Yellowstone National Park, some individuals are expressing greater concern about the occurrence of more significant earthquakes in the region. They question why these events have not been addressed by park authorities and media organizations. Graphs depicting Yellowstone indicate that the occurrence of these earthquakes had observable consequences on the park, since there was evidence of magma movement. There is another earthquake that has not been reported, which had a magnitude of 2.4. The graphs indicated a seismic event of greater magnitude than usual that occurred in the region, but no information or communication was provided regarding this occurrence. Upon the dissemination of the photographs, individuals began to inquire as to why this information was being withheld. There are hypotheses suggesting that the reason for not disclosing information could be to prevent causing anxiety among the public. Alternatively, others speculate that there might be ongoing events in the Yellowstone area that authorities are aware of but choose not to disclose. Dr. Poland stated that the earthquakes that have been observed are within the expected range of normal activity. The Yellowstone system exhibits high levels of tectonic activity, resulting in an average of around 1,500 to 2,500 earthquakes each year in the surrounding area. Typically, Yellowstone experiences between 100 and 200 earthquakes every month, primarily resulting from minor faults. The convergence of a fragile crust, elevated temperatures, numerous faults, and active subsurface water movement generates optimal circumstances for the occurrence of several smaller earthquakes. Scientists have recently stated that the animals residing in Yellowstone National Park have been engaging in migration. According to certain studies, animals have the ability to detect variations in electrical fields or the discharge of gases from the Earth. This is why some animals seek refuge when an earthquake is imminent. In the last 2 years, this supervolcano has demonstrated to scientists its ongoing activity. Researchers said that last year, 2 out of the 3 indicators signaling an imminent eruption were detected. These indicators consist of a rise in seismic activity and an escalation in the number of gas vents on the surface. In addition to this, researchers at the park have reported the emergence of new erupting vents and surface fissures. They have been compelled to shut down a boardwalk in the well-liked upper basin. Currently, researchers are monitoring the activity closely. Due to its potential for catastrophic eruptions, the supervolcano is under constant surveillance by scientists and governmental agencies. While the likelihood of another super eruption occurring in the near future is low, the potential consequences of such an event are immense. A super eruption could spew thousands of cubic kilometers of ash and pyroclastic material into the atmosphere, significantly impacting global climate, agriculture, and human health. Even smaller eruptions or hydrothermal explosions within the caldera could pose significant risks to the park and surrounding areas. The primary reason for monitoring the Yellowstone supervolcano is to protect public safety. Surveillance of the supervolcano also advances scientific understanding of volcanic processes and hazards. Yellowstone is a unique natural laboratory for studying geothermal and volcanic activity. By monitoring the volcano, scientists gain insights into the mechanics of caldera systems, magma movement, and the triggers of volcanic eruptions. This knowledge not only enhances our understanding of Yellowstone, but also improves our ability to predict and prepare for volcanic events worldwide. One of the primary tools for monitoring the Yellowstone Supervolcano is seismic monitoring. The Yellowstone Seismic Network, operated by the United States Geological Survey and the University of Utah, consists of over 50 seismometers distributed throughout the park. These instruments detect and record earthquake activity, providing data on the movement of magma and geothermal fluids beneath the surface. Increased seismic activity can indicate changes in the volcanic system and potential precursors to eruptions. Scientists also monitor ground deformation to detect changes in the shape of the Earth's surface caused by magma movement. The Yellowstone Volcano Observatory employs a combination of GPS stations, satellite-based interferometric synthetic aperture radar, and borehole strain meters to measure ground deformation with high precision. Uplift or subsidence of the ground can signal changes in magma pressure and movement, helping to assess the likelihood of volcanic activity. Geochemical monitoring involves analyzing the composition of gases and thermal waters at Yellowstone's geothermal features. The release of gases such as carbon dioxide, sulfur dioxide, and hydrogen sulfide can provide clues about magma movement and volcanic activity. By sampling and analyzing these gases, scientists can identify changes in the volcanic system and assess the potential for eruptions. Remote sensing technology, including satellite imagery and aerial surveys, plays a crucial role in monitoring Yellowstone's supervolcano. Satellites equipped with thermal imaging and spectrometers can detect changes in surface temperatures and gas emissions. The continuous monitoring of Yellowstone's supervolcano is integral to developing and maintaining early warning systems. By detecting signs of increased volcanic activity, scientists can provide timely alerts to governmental agencies and the public, allowing for preparedness measures and potentially saving lives. Effective communication and coordination among federal, state, and local authorities are essential to respond swiftly to volcanic threats. Surveillance data informs preparedness and mitigation strategies for potential volcanic hazards. Emergency response plans, public education campaigns, and infrastructure resilience measures are all based on the insights gained from monitoring the volcano. By understanding the risks and preparing accordingly, communities can reduce the impact of volcanic events on lives and property. Researchers have uncovered a previously unidentified source of partially liquefied rock that is large enough to fill the Grand Canyon 11 times over. The researchers employed seismic tomography to provide a comprehensive depiction of the entire volcanic plumbing system in Yellowstone, spanning from the Earth's mantle to the surface. Yellowstone National Park showcases a diverse range of geothermal phenomena such as geysers, mudpots, steam vents, and hot springs. This park is situated on top of a supervolcano that has had 3 catastrophic eruptions. Prior to this discovery, scientists were previously aware of the existence of a substantial magma chamber beneath Yellowstone National Park. This chamber was responsible for supplying the volcanic eruptions that occurred approximately 2 million, 1.2 million, and 640,000 years ago. The recent research, published in the prestigious journal Science, unveiled a further, more profound reservoir that is 4.5 times greater in size. The presence of a second magma chamber does not affect the likelihood of a major volcanic eruption at Yellowstone. According to seismologist Jamie Farrell from the University of Utah, these findings have little impact on the existing volcanic danger at Yellowstone. Nevertheless, these recent discoveries do furnish us, as well as other scientists, with the necessary information to enhance our comprehension of the process by which magma migrates from the Earth's mantle to the surface. According to Professor Fan-Chi Lin, a geology and geophysics professor at the University of Utah, there is a blob-shaped magma reservoir in the lower crust of the Earth underneath Yellowstone. This reservoir is located at a depth of 12 to 28 miles, or 19 to 45 kilometers, and has a volume of 11,500 cubic miles, which is over 11 times larger than the volume of Arizona's Grand Canyon. The magma chamber is composed of predominantly solid and porous rock, interspersed with pockets of molten rock. The researchers reported that approximately 2% of it was entirely liquefied. The upper and lower magma chambers are located above a geological phenomenon known as a plume or upwelling. This plume originates from the Earth's mantle, approximately 40 miles below the surface, and transports hot materials towards the surface. Scientists have previously hypothesized the presence of a subterranean reservoir of molten rock, known as a magma chamber, but were unable to definitively verify its existence. The researchers employed seismic tomography, a method akin to a CT scan, to visualize the subsurface by utilizing seismic waves that traverse the Earth. This technique enables the differentiation of rocks with different densities. In addition, they used local and remote earthquake measurements to visualize the entirety of Yellowstone's magma system. Earthquake swarms are sequences of seismic events that occur in a localized area over a short period of time, without a single dominant main shock. Unlike typical earthquake sequences, which consist of a main shock followed by aftershocks, swarms are characterized by numerous small to moderate-sized earthquakes. These swarms can last from hours to weeks and may vary in intensity and frequency. Yellowstone National Park has a long history of seismic activity, with thousands of earthquakes occurring each year. Most of these are minor and go unnoticed by the public. However, the park has experienced several notable earthquake swarms in the past, such as the 1985 swarm near Lake Hebgen and the 2008 swarm near Yellowstone Lake. These events have provided valuable data for understanding the geological processes at play in the region. The recent swarm of earthquakes in Yellowstone has captured widespread attention due to its intensity and duration. Beginning in late 2021 and continuing into 2022, the swarm has included hundreds of small to moderate-sized earthquakes, with magnitudes ranging from 1 to 4.5. The epicenters of these quakes are concentrated in the western part of the park, near the Norris Geyser Basin and the Yellowstone Caldera. The United States Geological Survey and the Yellowstone Volcano Observatory have been closely monitoring the swarm using a network of seismometers and other geophysical instruments. These tools provide real-time data on earthquake locations, depths, and magnitudes, allowing scientists to analyze patterns and assess potential hazards. The data collected during the swarm is crucial for understanding the underlying geological processes and for forecasting future activity. Yellowstone's earthquake swarms are primarily driven by the region's tectonic and volcanic activity. The park sits atop a hotspot, where a plume of hot mantle material rises towards the surface, causing the Earth's crust to stretch and thin. This process creates faults and fractures in the crust, which can lead to earthquakes when stress is released along these faults. In addition to tectonic forces, the movement of magma and hydrothermal fluids beneath the surface can also trigger earthquakes. As magma rises and exerts pressure on surrounding rocks, it can cause fracturing and seismic activity. Similarly, the movement of hot water and steam through the park's extensive hydrothermal system can induce earthquakes by altering the pressure and stress conditions in the crust. One of the primary concerns associated with earthquake swarms in Yellowstone is the potential for volcanic eruptions. While swarms can be a precursor to volcanic activity, it is important to note that the majority of swarms do not lead to eruptions. The United States Geological Survey and the Yellowstone Volcano Observatory closely monitor changes in seismicity, ground deformation, and gas emissions to assess the likelihood of an eruption. Based on current data, there is no indication that the recent swarm is leading to an imminent volcanic event. The recent earthquake swarm underscores the importance of public safety and preparedness in regions with significant geological activity. Residents and visitors to Yellowstone should be aware of earthquake risks and follow guidelines for earthquake safety. This includes securing heavy objects, having emergency supplies on hand, and knowing how to respond during and after an earthquake. The United States Geological Survey and the Yellowstone Volcano Observatory offer valuable resources and updates to help the public stay informed and prepared. The data collected during earthquake swarms in Yellowstone contributes to the broader understanding of volcanic and seismic processes. By studying these events, scientists can gain insights into the behavior of magma, the mechanics of faulting, and the dynamics of geothermal systems. This research not only enhances our knowledge of Yellowstone, but also informs the study of other volcanic and tectonic regions around the world. The Yellowstone Supervolcano is one of the most powerful and potentially destructive volcanic systems on Earth. Its past eruptions, the last of which occurred approximately 640,000 years ago, have reshaped the landscape and had far-reaching impacts. If the Yellowstone supervolcano were to erupt again, The consequences could be catastrophic, with significant damage on local, national, and global scales. The most immediate and severe damage from a Yellowstone supervolcano eruption would occur within the vicinity of the caldera. The eruption would likely begin with massive explosions that could eject thousands of cubic kilometers of volcanic material into the atmosphere. The force of these explosions could destroy everything within a 50 to 100 kilometer radius, including the park's infrastructure, wildlife, and any human presence. The pyroclastic flows, fast-moving currents of hot gas and volcanic matter, would incinerate and bury everything in their path, creating a lifeless landscape reminiscent of past eruptions. Beyond the immediate vicinity, the eruption would produce a colossal ash plume that could extend hundreds of kilometers.